Hello, Math 2 Extended. This video is for Unit 5, Lesson 4. We're going to be talking about some trig theory today. So everything we've done up to this point has sort of been computationally driven. Like we've wanted to calculate a side length or we've wanted to calculate an angle. But today isn't about calculations anymore. It's about the relationships between all of these different elements, between the trig ratios and the side lengths and the angles. And so it's not really about calculations today, though we will do a few. It's more just about sort of exploring some of these relationships. So if we have a diagram like this triangle at the right, we know that it has a leg of 5, the other leg has a length of 12, and the hypotenuse has a length of 13. We would like to write down each of these ratios. So when it asks you what the sine of A is, it's not asking you to calculate A, it's not asking you to calculate a side length, it's just asking you, hey, what's the sine ratio for angle A? So for angle A, the sine ratio would be the opposite side from A, which the opposite side is 12, over the hypotenuse, which is 13. So the sine of A is 12 over 13, and that's our answer. That's what it wants. It wants the sine ratio for angle A. The sine of angle B would be different though, because that would be from B's perspective, what is the opposite divided by the hypotenuse? And opposite from B is 5. So this one would be 5 over 13. So let's finish up looking at angle A, and then we'll go through and finish up angle B. So the cosine of angle A would be the side adjacent to angle A divided by the hypotenuse, and the tangent of angle A would be the side opposite angle A divided by the adjacent leg, TOA. Tangent is opposite over adjacent. So from A we have 12 is opposite and 5 is adjacent. So that's the trig ratios for angle A. For cosine of angle B, we need the adjacent leg to B divided by the hypotenuse. And for tangent of angle B, we need the side opposite B divided by the leg adjacent to B. So if you're looking at all of these fractions, you might notice that this one and this one are the same, that the sine of A is equal to the cosine of B. You might also notice that this one is equal to this one. That is that the cosine of A is equal to the sine of B. I'm going to write that down. Sine A equals cosine B. Sine B equals cosine A. And then if you're looking at those tangents, the thing that you might notice is that you might notice that these are reciprocals. So the tangent of A is the reciprocal of the tangent of B. So let's formalize that a little bit. Another thing that you might notice looking at this triangle is that we do know that angle A and angle B together add up to 90. All of the angles add up to 180, and since angle C is 90, that means A plus B has to also be 90. All right, so cofunction identity. A second ago, we said that the cosine of angle A is equal to the sine of angle B. Those are both equal to 5/13, and that the cosine of angle B is equal to the sine of angle A, and that the tangent of angle B is equal to 1 over, or the reciprocal of, tangent of A. So if we combine those equations that we wrote with the idea that A is equal to 90 minus B, what we end up with is this formula. The cosine of theta is equal to the sine of 90 minus theta. That is exactly equivalent to this equation right here. The cosine of B is equal to the sine of 90 minus B, which is A. So that's called a cofunction identity. So the cosine of theta is equal to the sine of 90 minus theta. And then the tangent coangle identity would be that the tangent of theta is equal to 1 divided by the tangent of 90 minus theta. So if we know information about the sine of 31.9, the cosine of 31.9, and the tangent of 31.9, we are also able to calculate or to give a lot of information about the angle 58.1 degrees. So if I want to know the sine of 58.1, it's going to equal the cosine of 31.9. So the value of the sine of 58.1 would be 28 over 53. If I want to know the tangent of 58.1, it's going to be the reciprocal of the tangent of 31.9. It's going to be 45 over 28. When we're working computationally, sine, cosine, and tangent are the trig functions that we commonly use, but there are also three less commonly used trig ratios, the secant, the cosecant, and the cotangent. They're just the other combinations or the other ratios that are possible for that right triangle. So the cosecant of theta, so cosecant is spelled like this, but we abbreviate it as CSC, like cosecant. The cosecant of theta is the hypotenuse divided by the opposite. The secant of theta is the hypotenuse divided by the adjacent. And the cotangent is the adjacent divided by the opposite. So for this triangle, we're going to give all 6 trig ratios for angle theta. So theta is the angle up at the top of the triangle, so that's our vantage point, that's our reference angle. We're going to give the sine of theta, the cosine of theta, the tangent of theta, the cosecant of theta, the secant of theta, and the cotangent of theta. Now sine, cosine, and tangent are easy peasy ones. So the sine of theta is opposite over hypotenuse. That kind of looked weird, sorry. Root 117. The cosine would be adjacent over hypotenuse, and the tangent would be opposite over adjacent. Now, sometimes these values can be simplified. For example, if you look at the tangent of theta, hopefully you can see straight away that that is equivalent to 3/2. If you were to type 9 over root 117 in your calculator would turn it into 9 root 117 over 117. Your calculator is doing something called rationalizing the denominator. And so I don't really care if you rationalize the denominator or not. Probably I should care, but I don't. The reason that denominators got rationalized is that they historically didn't have calculators, and it was easier to perform operations if your radical was in the numerator, so they would rationalize it. The reasons that they rationalized don't apply as much anymore because of our calculators. But what is good to know is that if you are answering an ACT question or something and you get this as your answer, you may not see that on the multiple choice choices. You would see this. So you need to be aware that rationalization is a thing. Your calculator can rationalize it for you, but you need to realize that it's a thing. So really quickly, I just want to show you how your calculator rationalizes. If I have 6 over root 117, what the calculator does is multiply by a fancy number 1, which is a root 117 over root 117. So the top of this would be 6 root 117. And the bottom, when I times a root 117 by another root 117, it just becomes the number 117. So you can see how your calculator went from this to this. That's called rationalizing. Okay, so we have given the sine and the cosine and the tangent. Let's do the cosecant, secant, and cotangent. So I have those listed over here since those are new to us, so that we can refer to them. So the cosecant is hypotenuse over opposite. So that will be root 117 over 9. The secant is hypotenuse over adjacent. That will be root 117 over 6. And the cotangent is adjacent over opposite, which is 6 over 9. And we can reduce that one or simplify that one to 2/3. thirds. So I want to know, what relationship do you notice between the sine and the cosecant? What relationship do you notice between cosine and secant? And what relationship do you notice between tangent and cotangent? And hopefully what you notice is that they are reciprocals of each other. So here are our reciprocal identities. Cosine of theta is 1 over the sine of theta, which is another way of saying reciprocal. Secant of theta is 1 over the cosine of theta, and cotangent of theta is 1 over the tangent of theta. On your test, the two things that I will give you are, I will give you this little memory device, and I will give you these reciprocal identities. So that is all information that you will have on your test. So in other words, if I know the cosecant of theta is 1 over sine, I know that it's hypotenuse over opposite because I know that it's the reciprocal of this guy. I don't know why I put it. It's kind of not really a times there. Anyway, so you can get all of the information from this and you'll have that on your test. Okay, so let's answer a couple of questions. If I know the cosine of beta is 5/8, what is the secant of beta? Well, those are reciprocals. So the secant of beta would be 8/5. If I know the sine of gamma, this is the Greek letter gamma. If I know the sine of gamma is 1 over root 2, then that means the cosecant of gamma would be the reciprocal. So that would be root 2. You could write root 2 over 1, but it's not necessary to write over 1. It is just root 2 if it's root 2 over 1. Okay, and finally, we know that the cotangent of alpha is root 3. I want to know what's the tangent of alpha. Well, those two things are reciprocals, so the tangent of alpha would be 1 over root 3. Okay, here I want to just revisit the cofunction identities. So if I want to know the cosine of theta, it's the sine of 90 minus theta. Cosine is the cofunction of sine. Here's two more though. If I want to know the cosecant of theta, cosecant is the cofunction of secant. So it is equal to the secant of 90 minus theta. The cosecant of b is equal to the secant of a, which is 90 minus b. And then finally, cotangent is the cofunction for tangent. So the cotangent of theta is 90 minus the sine of theta. So the cotangent of b would equal to the tangent of a. All right. So those are our cofunction identities. All right, so it turns out that knowing just one of the trig ratios for an angle gives us enough information to figure out the ratio, any of the 6 trig ratios for that angle. A diagram in the Pythagorean theorem can help you figure out all of the others. So we know that the sine of alpha is equal to 4 over 8. Well, sine is the ratio of opposite over hypotenuse. So we're going to build a triangle with that ratio. So I'm going to just put the alpha down here at the bottom. We've got our 90-degree angle. The side opposite alpha is 4, and the hypotenuse is 8. Now, the 4 over 8 is a ratio. So we could have done 8 and 16. We could have done 1 and 2. We could do any combination that has that ratio of 4 to 8 or 1 to 2. But I usually just write whichever one they gave me and call it a day. So let's see. Our goal here is to write down the sine of alpha. Well, we already know that one. It was given to us. The cosine of alpha, the tangent of alpha. We want to also write down the cosecant of alpha, the secant of alpha, and the cotangent of alpha. Well, right away, I can tell you the cosecant because I know cosecant is the reciprocal of sine. So that means the cosecant is 8 over 4. And both of these reduce. That one reduces to 2, that one reduces to 1/2. All right, so let's see if we can figure out the other ones. Well, cosine is adjacent over hypotenuse. Well, I can certainly write down the hypotenuse, but to finish writing cosine, I need to know the adjacent side. So we can use the Pythagorean theorem to figure out the adjacent side. We know that the adjacent side, I'm going to just call it A for adjacent, A squared plus the other leg squared is equal to the hypotenuse squared, which means that A squared is equal to 64 minus 16, which is 48. And that means that that adjacent side is 4 root 3. So I can finish up my cosine, and it is 4 root 3. If I simplify that either in my head or in the calculator, I get root 3 over 2. Well, now that I know the cosine of alpha, the secant of alpha is very easy. It's just the reciprocal of that, which is 2 over root 3. If you chose to type it into your calculator or simplify it, you would get 2 root 3 over 3. I'm okay with either of these answers. Either of those is fine. Okay, let's go to the tangent of alpha. The tangent of alpha is the opposite leg of alpha divided by the adjacent leg to alpha. So this would reduce to 1 over root 3, or if you use your calculator to rationalize it, it's root 3 over 3. The cotangent of alpha is going to be the reciprocal. So it actually is easier to do the reciprocal from the unrationalized version. So cotangent of alpha is root 3. It is also equal to 3 over root 3, but that is just root 3. So anyway, it's easier, kind of easier to do the reciprocal from this version. All right, so we wrote down all of the other trig ratios. Please note, it never asked us to find alpha. It never wanted to know the size of the angle. This is all about just writing down the ratios. But by the way, alpha is 30 degrees, in case you're wondering. Okay, here was one for you to try on your own if you were in class. I'll hurry and write it out for you. We know that the tangent of beta is 3 over 4. Well, tangent gives us opposite over adjacent ratio. So we're going to treat the opposite side like it has a length of 3 and the adjacent like it is a length of 4. So if we try to find the hypotenuse, which we're going to need when we write down the sine or the cosine, I'm going to call it C, even though it's I'm going to call it C just because the Pythagorean theorem uses C for the hypotenuse. So if we're calculating C, it would be 3 squared plus 4 squared equals C squared. 25 is equal to C squared. So that means the hypotenuse is 5. All right, so now we can write down our ratios. The sine of beta, opposite over hypotenuse. The cosine of beta is adjacent over hypotenuse. We already knew the tangent of beta. And we can also write down the cosecant of beta. Cosecant is 1 over sine, or the reciprocal of sine. The secant of beta is 5 over 4, and the cotangent of beta is the reciprocal of tangent. That's 4 over 3. Something I would like to point out, sometimes people can't remember, is cosecant 1 over sine or 1 over cosine. And so just what I would like to point out is that sine goes with cosecant and cosine goes with secant. So like the C and the S kind of switch. If that helps you, you can think of it that way. Like I always think they always have a C. So if I'm doing sine, I know it has to be cosecant because there always has to be a C. If I'm thinking about cosine, I know the reciprocal is secant because I know there's just one C involved, and that the tangent doesn't have a C, so it's cotangent. It has a C. So when we're thinking about which ones are the reciprocals, there's always a co one involved. There's always one C involved. Okay, so here's one. It says, what's if the cosine of theta is 3/4? What is the cotangent of theta? This is like our last problem, but it's just not quite as involved. We don't have to list all of the ratios. We just have to find the one we're after. Here's my theta. The cosine of theta is adjacent over hypotenuse. So this other leg is not 3 because in a 3, 4, 5 triangle, the 5 is the hypotenuse, but we know our hypotenuse is 4. So to calculate this opposite side, from theta, we're going to do, I'm going to call it b. So we would do 3 squared plus b squared is equal to 4 squared. That means b squared is 7 because we're doing 16 minus 9. And that means b is root 7. So our opposite side is root 7. And what our goal is to write the cotangent of theta. Well, we know that tangent is opposite over adjacent. So cotangent is adjacent over opposite. And so the cotangent of theta is adjacent over opposite. 3 over root 7. It's fine if you want to leave your answer that way. If you typed that into your calculator, it would look like 3 root 7 over 7. Okay, so we want to explore a couple of relationships between different trig functions now. This triangle has a common mathematical convention. If we have our vertices or our points labeled A, B, and C, we label the sides across from them with the same letter but lowercase. So this side across from B is little b, the side across from C is little c, and the side across from A is little a. Okay, so I want to know what is the sine of B divided by the cosine of B? Well, if I'm thinking about angle B, the sine is B over C, and the cosine of B is A over C. I think when we're dealing with fractions, we're all pretty comfortable with that if we had a 2b divided by a 2a, we could reduce the 2's to get b over a. But it works with division as well. If I have b divided by 2 and a divided by 2, I can cancel out the divide by 2. It's really the same as having this 1/2 b times 1/2 a. And we don't need to write it that way, but it maybe makes it easier to see. But we can definitely cancel dividing by if it's the same in the top and the bottom. So if I have a b divided by c divided by an a divided by c, I can reduce the dividing by c to end up with b over a. So the sine of b divided by the cosine of b is b over a. Well, look at angle B. B over A is the tangent of B. So that's interesting. So let's think about the cosine and sine of A. The sine of A is A over C. The cosine of A is B over C. I can reduce that over C to get A over B. But that is the tangent of A. So this is called the tangent identity, and that is that the tangent of any angle is equal to the sine of the angle divided by the cosine of the angle. Like, generally speaking, we can cancel out the hypotenuse is kind of what's happening here. So if you know that the sine of an angle is, sine of theta is 3/7. Oh, let's see. Sorry, I don't want to do 3/7. If you know that the sine of theta is 12 over 13, and you know the cosine of theta is 5 over 13, you can get the tangent of theta very quickly by just doing sine divided by cosine, 12 over 5. So that's, without having a triangle, that's kind of one way you could think about tangents. Okay, and there's my meme version. The tangerine divided by the cotangerine is the tangerine. All right, here we go. Our next fancy identity is called the Pythagorean identity. So I'm going to show you where the Pythagorean identity comes from. So we're going to start with the Pythagorean theorem for this triangle. So we know from the Pythagorean theorem that a squared plus b squared is equal to c squared. Well, a mathematician was like, I wonder what that means. They wanted to figure out another relationship with respect to the angle theta. So somebody said, some famous mathematician sometime, they said, what if we divide this side, both sides of this equation by a c squared? Well, on this left side, c squared divided by c squared is 1. And one of the properties of division, if I have an a squared plus b squared divided by a c squared, I can write that as an a squared divided by c squared plus a b squared divided by c squared. Each of those terms is divided by c squared. Well, if we apply our exponent property, this is the same as the fraction a over c that's being squared, and this is the fraction b divided by c that is being squared. So now let's connect this back to theta. Think about that angle theta. If I have the ratio a divided by c, a is the opposite and c is the hypotenuse. So that ratio a divided by c is the sine of theta. And if I think about b divided by c, well, b is adjacent to theta. So the b divided by c is the same as the cosine of theta. So this gives us our Pythagorean identity. The sine of theta squared plus the cosine of theta squared is equal to 1. It's an important identity that gets used a lot in higher math. So we're going to use this to help us solve a problem or two. If I know that the cosine of alpha is root 3 over 2, what would the sine of alpha have to be? And again, we could solve this by setting up a triangle and all that stuff, but we could also use our Pythagorean identity. We know that the sine squared of alpha plus the cosine squared of alpha is equal to 1. So if I substitute root 3 over 2 for the cosine of alpha, I know that these two things have to add together to give me 1. Well, the sine of alpha squared, root 3 divided by 2, if I square it, it is the same as 3/4. So if I subtract the 3/4, I get the sine squared of alpha is equal to 1/4. And when I root both sides, I get the sine of alpha is equal to 1/2. So the sine of alpha is 1/2. Now, hopefully in your little brain, you were like, Miss Bricky, you rooted both sides of an equation. We should have a plus or minus symbol there. And that is true. We have not talked about what it means for a sine to be negative yet. So right now, we'll just say that the sine of alpha is 1/2. But in lesson 6, we will be talking about what the heck the negative means right there. So also it could be in a decimal form. If we have the sine of theta is 0.8, we could calculate the cosine of theta easily. We know that that sine squared, so 0.8 squared plus the cosine of theta squared is equal to 1. So 0.8 squared is 0.64. So if we subtract, we get the cosine of theta squared is equal to 0.36, which means the cosine of theta is 0.6. Now, again, technically it's also negative 0.6, but we'll talk more about the negatives later, so you don't need to worry about it for now. All right, the last one asks us, what about the tangent of theta? Well, tangent is sine divided by cosine. So let's think about that for this last example. We know that the sine is 0.8. If we divide it by the cosine, 0.6, we will get the tangent. So the tangent of theta, if you do it in your calculator like this, it will give you a fraction, or the decimal version would be 1.3 with the 3 repeated. That is the tangent of theta. Okay, we're almost done. This is our last example. We're going to be talking a little bit about inverses again. So I just want to remind you quickly about inverses. Anytime you are looking at an inverse, what that is doing, it's asking you to calculate the angle that has a sine of 4/3. Oh, I wrote 3/4. I said 4/3 and I wrote 3/4. So anytime you're using an inverse, it's talking about an angle. So if I have this triangle, which angle, alpha or beta, is the tangent, the inverse tangent of 4/2 root 3? So remember, tangent ratios are opposite over adjacent. So we're trying to figure out which angle is opposite 4 and adjacent to 2 root 3. So this is alpha. The inverse tangent of 4 over 2 root 3 is the angle alpha. These are composite functions. It's a function inside of another function. We have worked with some compositions this year a little bit. So if I have an inverse tangent function inside of a secant function and I want to calculate it, just as with other types of functions, we're going to evaluate starting with that inner function. We're going to think about what angle are we talking about? Well, the inverse tangent of 2 root 3 over 4, this is different than the one we just talked about. Inverse tangent of 2 root 3 over 4, I'm looking for the angle that is opposite to root 3 and adjacent to 4. So the angle that is opposite to root 3 and adjacent to 4 is angle beta. So this whole little part is just saying, hey, beta is our angle. We want to know the secant of beta. Secant is 1 over cosine. So the secant is hypotenuse over adjacent. So the secant of the inverse tangent of 2 root 3 over 4 is the same as the secant of beta, which is the hypotenuse of the triangle divided by the adjacent side of the triangle. That would reduce to root 7 over 2. Let's try this one. Find the exact value of the sine of the inverse cosine of 2 root 3 over 2 root 7. So the cosine inverse, we're going to start with that inner function. The cosine inverse of 2 root 3 over 2 root 7 is telling me that I'm thinking about the angle that is adjacent to 2 root 3. That's telling me that I'm thinking about the angle alpha. My question is, what's the sine of that angle? So my question is, what's the sine of alpha? Well, the sine of alpha is opposite over hypotenuse. If you rationalize that, it is 2 root 7 over 7. Again, it's not important that you rationalize necessarily, but if you want to rationalize it, your calculator can help you. All right, so here's 2 more. What is the sine of the inverse sine of 2 root 3 over 7? So we just talked about that was a cosine. The inverse sine of 2 root 3 over 2 root 7 is telling me that I am looking for the angle opposite the 2 root 3. So this is angle beta, and I want to know the sine of angle beta. Well, the sine of angle beta is 2 root 3 over 2 root 7. Hey, wait. That's what I started with. Did you notice that the sine and the inverse sine, those are inverse operations. They undo each other. So if I'm taking the sine of the inverse sine of something, I'm just going to get the something back as my answer, with some nuance that we'll talk about in lesson 6. Our last question here, what is the value of the inverse cosine of the cosine of alpha? Well, the inverse cosine undoes the cosine. Those are inverse operations. So my answer to this would just be alpha. All right, we did it. That was so much fun. Very theoretical today, so it's not about computations. It was about exploring relationships. Sometimes for people that's a little bit trickier to wrap your head around, but I think if you practice it up, it's really just about understanding the definitions and a few relationships. And so let me or your teacher know if you have any questions. Thank you so much.